So, Jai Hind students, today we are going to discuss a special type of diode, that is Zener diode. So, Zener diode are the special types of PN junction diode which are used for a specific application. A Zener diode is designed in such a fashion that if we allow to pass a current, that means if it is designed in such a fashion that it is designed to reliably allow a current which flows in the backward direction when a certain set of reverse voltage, which is known as the Zener voltage, is reached. So, some of the Zener diodes have a sharp, highly doped PN junction with a low Zener voltage. In this case, the reverse conduction occurs, which is due to the electron quantum tunneling in the short space between P and N region, because Zener diode is highly doped function. So, the depletion region is very, very thin, and this is known as the Zener effect. So, diodes with a higher Zener voltage have a more gradual junction, and their mode of operation also involves the avalanche breakdown. Both types of the breakdowns are present in Zener diode, with the Zener effect predominantly at a lower voltage and avalanche breakdown occurs at a higher voltage. So, Zener diodes are optimized for the operation in the breakdown region. So, Zener diode is quite similar. If we talk about the analysis of the Zener diode, so it is quite similar to that of your ordinary PN junction semiconductor diodes. So, the first state of the diode, the first state of the diode must be determined, and which is followed by the substitution of an appropriate model and determination of the other unknown quantities in the network. So, this is how we do the analysis of the Zener diode circuits. So, if we connect the Zener diode in the forward biased state, then it behaves as an ordinary PN junction diode, and in this circuit, in this case, in this characteristic, we can see that when we apply a forward bias across the Zener diode, then up to, because this diode is considered, the material for manufacturing of the Zener diode is considered to be the silicon material. So, up to the value up to the value of 0.7, that is the barrier potential voltage, the diode does not conduct, and as soon as it the value of the barrier potential overcome, then the diode starts conducting. So, the current starts flowing through the diode after the barrier potential voltage. Whereas, if we connect the Zener diode in the reverse bias condition, then it behaves as a voltage regulator, which is the most important application of the Zener diode. So, the Zener diode is known for the application of the voltage regulator. So, the use of the Zener diode as a voltage regulator is common, that the three conditions surrounding the analysis of the basic Zener diode are considered. So, basically we are going to discuss the three major conditions. First case, when we consider both Vi and the load resistance, they are considered input voltage and the load resistance, both are to be considered as fixed. And in second case, we can fix up the input voltage, we can fix up the input voltage and keeping the load resistance variable. In third case, variable Vi and Vi can be varied and RL kept at the fixed value. So how do we start the analysis? So the first point is analysis has been divided into two steps. So first of all, we have to determine the state of the Zener diode, that whether it is in on state or it is in off state. So if the value which is appearing across the Zener diode is greater than or equal to Vz. Vz is the value of the designed value of the Zener diode, of a particular Zener diode. So if this terminal, let us mark this terminal A and B. So if the voltage which is appearing across this terminal VAB, if it is greater than or equal to Vz, then Zener is on. And when Zener is on, then it will be replaced by a battery of Vz. But in case if this VAB is less than Vz, then Zener diode will be in off state and it will be open circuit. So this is how, first of all, we need to find out that whether the Zener diode is greater than or equal to Vz. So for that we have to, that can be done by calculating the voltage across this. So the first step, remove the Vz from the circuit and find out the voltage across the terminal A and B. And as we can see that the voltage across AB is in parallel with the load resistance, that means these two voltages must be equal. So I can say that VAB is nothing but VL, and which is the voltage that is appearing across the load resistance RL. So by using the voltage divider theorem, we can calculate this value. So we can write VL is equal to RL divided by R plus RL times VI. So what is voltage divider theorem? Voltage divider theorem can be used in like that the voltage across the value of the resistance across which we need to calculate the voltage divided by the summation of all the resistances present in the circuit. So by using this equation, we can calculate the VAB. Now we compare this voltage VAB with the Vz, the Zener voltage. So if it is greater than or equal to Vz, then diode will be in on state. If it is in on state, it will be replaced by a battery of value Vz. But if it is, this value is less than Vz, then it will be in off state, and off means open circuit. So Zener diode will be replaced by an open circuit. So next step is substitute the appropriate equivalent circuit and solve the desired unknowns. So because the voltage across the parallel elements must be same, so we can say that VL must be equal to Vz, because these two are parallel and we know that in parallel voltage remains same. So that's why we can say that Vz is equal to VL. Zener diode can be calculated by using the equation. Here we can see in the circuit that the net current is IR, the total current is IR, and which is divided into two currents, that is IZ and IL. So the net current will be, the equation of the current will be IR is equal to IZ plus IL. So IZ can be calculated by using this equation, that is IR minus IL. And the power which is dissipated across the Zener diode will be given by PZ is equal to Vz times Iz. Pz times IZ. So this is the first example. So here this is the case 1. We have considered the case 1 where Vi and RL both are fixed. Both are fixed. So first of all, in this particular network, what is giving? Vz is giving PZM. PZM means maximum power across the Zener of the Zener diode, which it can withhold. That is giving, that is 30 milliwatt. Value of the load resistance 1.2 kilo ohm is given. Vi is given, and what we have to calculate? We have to determine VL, VR, IZ and PZ. So this is the A part. So let us start solving this problem. So my first step is remove the Zener diode from the network. So remove Zener and calculate VAB. So if we remove the Zener diode from here, from this terminal VAB, and calculate the voltage across the terminal VAB, so we can see that this and this VAB is in parallel with the load resistance. So VAB is nothing but equal to the voltage which is appearing across the load resistance RL. So I can say that VL is equal to VAB, and that is equal to RL by R plus RL times Vi. So if we calculate this, so it will be equal to 1.2 into 10 to the power of 3 divided by 1 plus 1.2 into 10 to the power of 3 times 60. So this will be 1.2 into 16 divided by 2.2 volts. So the calculated value comes out 8.73 volts. So now compare this value with Vz, and Vz is given as, in the circuit we can see that Vz is 10 volts and VL comes out to be, or VAB is nothing but VAB is 8.73 volts. So if we compare to, so we find that VL is equal to Vz. Why? Because this VAB is less than Vz. So your diode will remain in the open circuit state. So this will be the equivalent circuit. So diode will be, Zener will be off. Zener will be in off state. That means open circuit. That is open circuit. So if it is an open circuit state, so this will be your equivalent circuit. So now we have to calculate the various parameters. So what will be the value of VL? VL will be equal to VAB, because these two are in parallel. So VL comes out to be 8.73 volts. Now we have to calculate the value of VR. VR is the voltage which is appearing across this resistance. So VR will be equal to VI minus VAB or VL. So VR is equal to VI minus VAB or VL. So this will be equal to 16 minus 8.73 volts. So the value comes out 8.27 volts. Now, what will be the value of Iz? Because this is open circuit, so Iz must be equal to 0. No current will be allowed to flow through the load resistance because it is open circuit. So, Iz comes out to be 0 ampere. And what will be the power? Power is nothing but the voltage multiplied by current. So, across the Zener power will be equal to the Zener voltage times Zener current. And Zener voltage is 10 volts, but the current across the Zener diode is 0. So, power will be equal to 0. So, in this complete problem, we have seen that diode does not come in the on state because the value across the Zener diode is less than the Zener designed value of the Zener diode, that is Vz. So, that if because the value is less than 10 volts, that is the Zener voltage, our Zener diode is in off state throughout the program. Now, we have to repeat the same problem by changing the, so in order to make the Zener diode, there are the 2-3 cases. First is we can change the input voltage, or we can change the load resistance, or we may change the resistance in the circuit. So, either of the variable can be changed, and by changing that we may get the circuit, so that our Zener diode can come in the on state. So, for doing that, so we are repeating the same problem by replacing the value of 1.2 kilo ohm by 3 kilo ohm. So, instead of using 1.2 kilo ohm, now we will repeat the same problem by using RL is equal to 3 kilo ohm. Right. So, this is the second case. In the second case, remove the Zener diode from the circuit and calculate the voltage across this terminal A and B. So, that is equal to RL divided by R plus RL. So, now the value of RL has been changed from 1.2 kilo ohm to 3 kilo ohm. So, if we calculate this value, we get the voltage, that is VAB, that is equal to 12 volt. And if we compare this VAB, so VAB, because now VAB is greater than VZ, because VAB is 12 volt and VZ given as the 10 volts. So, that is why our Zener diode will come in the on state. So, Zener diode will be on, and if it is on, it will be replaced by a battery of VZ with the polarity marked like as shown in the circuit. Why we have shown the polarity like this? Because we know that Zener diode works as a voltage regulator in the reverse bias state. So, that's why, that's the reason we have taken this as the positive sign and the this as the negative sign. Okay. So, once we calculate the value of VAB, because Zener diode is in on state, so the equivalent circuit will be like this. So, Zener diode will be replaced by a battery of VZ. So, now because this arm is in parallel, this VZ comes in parallel with the VL. So, and we know that in parallel voltage remains in same conditions, value of the voltage remains same. So, that's the reason your VL will be equal to VZ, that is 10 volts. So, this is how it regulates the voltage. So, your output voltage will be equal to now 10 volts. In the previous case, it was equal to 8.7 because that value was less than VZ, and in that case your Zener diode did not come in the on state. So, output will be equal to whatever across the Zener diode, and Zener diode remains in the off state, that is open circuit. So, now in the second case we have to calculate VR in the circuit. VR will be equal to how much? This VI minus VAB, which is now in this case it will be VZ. This. So VR is equal to VI minus VL or VZ. So that will be equal to 6 volts. Now what will be the value of IL? IL will be equal to VL by RL. So that is equal to 3.33 milliampere. Total current which is flowing through this is IR, and IR is equal to VR by R, where VR is 6 volts and R is 1 kilo ohm. So IR will be equal to 6 milliampere. So IZ will be equal to how much? IR minus IL. IR is 6 milliampere and IZ is 3.33. So if we subtract these two values, so output will be equal to 2.67 milliampere. So the power will be equal to IZ times VZ. So that is 26.7 milliampere. So here we can see that the value is less than 30 milliwatt. That was the giving. So that was the upper limit, that this much amount of the power can be dissipated across the diode. So if the value is less than that, your diode is in a safe zone. So now consider the second case. In the second case, VI is fixed and RL is variable. So whenever we would like to calculate the range, we always start with the step 1, where we remove the Zener diode from the terminal A and B, and calculate the value voltage across this VAB and compare this value with the VZ. Because now we would like to find out the range of RL in this particular case. So we want the minimum value of the RL which can make our Zener diode in on state, and the maximum value of the RL, so that the current which is flowing through the load resistance is within the maximum, within the range. That is, if IZ max is given, then that value across the load resistance must be less than that IZ maximum. So this is how we can find out the range. So first step, I need to calculate the minimum value of the load resistance. For that, we use the voltage divider theorem. So from this equation, we can calculate the RL minimum. So because we want to keep our Zener diode is on on state, so VL or VAB must be equal to VZ, and which is known to us, and we don't know the range of the RL, so RL minimum can be calculated. So from this voltage divider theorem, using step 1, we can calculate the value of RL minimum. So that is RL minimum plus R. So by manipulating this, we can calculate the value of RL minimum from using this equation. Now we know that this voltage is fixed, this resistance is a fixed value, so and VZ is also a fixed value, but this load resistance is variable, and voltage which is appearing across this load resistance, that is also fixed. So we can say that your VL is equal to VZ, and that will be equal to RL times IL, and this RL is a variable value. So if RL is minimum, then IL should be maximum, then only we can get this value VZ, a fixed value. So once we calculate this RL minimum, then IL maximum can be calculated, because this is known to us now from using this equation, and VZ is also known to us. So by using this equation, IL maximum will be equal to VL by RL, which is nothing but VZ by RL minimum. So this is how we can calculate the maximum current flowing through the load resistance. Now the second case is we need to calculate the RL maximum. So for calculating RL maximum, we have to consider the two equations. One is this VI is minimum fixed, this voltage which is appearing across this resistance, that is VR, this is again fixed, because the current across this will be a fixed value. So Vi minus Vz. So Vi is equal to Vr plus Vz. So from this equation we can calculate the value of Vr, that is Vi minus Vz. And once Vr is known to you, we can calculate the value of IR, which is again a fixed value because resistance is also fixed. Now IR can be calculated from this equation, VR by R, and this is a fixed value. Now we know that if IR is fixed, and that is consisting of the two components, that is IZ plus IL, and because my RL is variable, that means this current is also variable, and we know that VL is equal to IL times RL, and VL is a fixed value. That means if IL is minimum, then RL will be maximum. So IL is minimum and RL should be maximum, and we are interested in finding out the RL maximum now. So first we need to calculate the IL minimum. So how do we calculate IL minimum? IL minimum will be equal to this RL IR. This is IR. So IR is a fixed value, that is equal to IZ plus IL. And if this IR is a fixed value, if it is this is a fixed value, then and we are interested in finding out IL minimum. So IL, for finding out IL minimum, we must know IZ maximum. So if this IZ maximum is known to you, IR fixed is known to you, IL minimum can be calculated. And once IL minimum can be calculated, your RL max can be calculated by using this equation. So this is how we can calculate any variable value, means the minimum and maximum value, by using this process. So importantly, we have to keep in mind the two things. One is the voltage divider theorem for finding out the minimum value of any variable, and second is the Vi is equal to VR plus Vz, and third is IR is equal to IZ plus IL. So by keeping these three equations in mind, we can calculate any minimum and maximum, any range of the variable. So this is how we can calculate the problem. Second case is the third case is when we are having variable Vi and RL fixed. So here we need to calculate the range of this Vi. So again, Vi minimum can be calculated. Vi minimum can be calculated by using the voltage divider theorem, by removing the voltage across this. So Vi minimum can be calculated by using the voltage divider theorem. So that is VL is equal to VAB, that is equal to Vz, and that is nothing but RL divided by R plus RL times Vi minimum. So by using this equation, we can calculate the value of Vi minimum. So once we calculate the Vi minimum, now we need to calculate Vi maximum. Here, because this value is variable, so if this is maximum, if Vi maximum, then, and this Vz is fixed value, so Vi is equal to Vr plus Vz, and this Vz will always be a fixed value. So I need to calculate, if suppose I want to calculate Vi maximum, then this Vr should be maximum. So if Vr is maximum, then IR will also be a maximum value. So once we calculate the IR maximum, so what is my IR maximum? IR maximum, because here your load resistance is fixed and voltage across this will be equal to Vz. So that means your IL will also be fixed So IL is fixed. So IR maximum will be equal to what? When your Zener current will be maximum. So once we can calculate this IR maximum, once we calculate this IR maximum, we can calculate easily, we can calculate the VR maximum, which is equal to IR maximum times this resistance R. R is fixed. So once you calculate the VR maximum, once you calculate this VR maximum, VI max can be calculated by adding this value with VZ. So this is how we can calculate the VI max, that is equal to IR max times R plus VZ. So again, here we can see in the third case also, we have calculated the two variables, that is VI minimum and VI maximum. So for VI minimum, we have calculated the value using the voltage divider theorem, and for VI maximum, VI minimum we have calculated, minimum value we have calculated by using step 1, that is the voltage divider theorem, by removing the diode from the terminal A and B, and this maximum value can be calculated by using these two equations. VI is equal to VR plus VZ and IR is equal to IZ plus IL. We just need to keep in mind that at what time which value will be maximum and the other value will be minimum. So this is how we can, by using these analysis, we can solve any problem. Thank you. Jai Hind.